Alright, so let's now talk about electrolytic cells. Okay, so last time we talked about galvanic or voltaic cells. Those are cells where you run a redox reaction in separate compartments so you can generate electricity, right? Now, in an electrolytic cell, what we have is the opposite. We have a redox reaction that is not spontaneous, but we want it to run. Okay, so if we want it to go, if we want to force it to go, we apply electricity instead. And so that setup is called an electrolytic cell. So you have a non-spontaneous reaction. So if you calculate the cell potential for that, it's going to be negative. If you want that actual reaction to occur, you have to force it. And so you apply an external voltage, okay? So you do electrical work. The external voltage that you have to supply must be larger than the absolute value of the cell potential. Remember, it's negative. It has to exceed that, okay? And uh, as far as terminology is concerned, where the oxidation takes place, you still refer to that as the anode. Okay, so it's always, regardless of whether it's a galvanic or electrolytic cell, oxidation is always said to take place at the anode, and reduction takes place at the cathode. Except that this time, the positive and negative terminals of your cell are switched in terms of the assignment of positives and negatives. So we say the anode this time is positive and the cathode is negative. Remember, in a galvanic cell, oxidation takes place at the anode and the anode is negative, right? That's where the electrons come out of. Well, let's try to understand why the plus and minus is switched here. Let's say you wanted copper ions to deposit at a piece of copper metal, okay? And let's say that process for the particular reaction you're interested in, that doesn't happen, so we want to force it by passing electricity through it. So let's say copper picks up 2 electrons to give you copper. Is that oxidation or reduction? Reduction, right? Now, where would that take place? At the cathode. So if you have a cathode, if you have copper ions, and you want it to pick up electrons, okay, what voltage must you have on this electrode right here? You have to make this negatively charged. You hook this up to the negative terminal of your battery. So you have a battery right here. The negative terminal of the battery is hooked up to that, okay? So we say that the negative terminal of your electrolytic cell, okay, and this is not, circuit's not complete here, but you say if you want your copper to be reduced, then it has to be at the negative terminal, okay? So the negative terminal of your electrolytic cell is where the cathode is. It's where the reduction takes place, okay? So this is where it picks up the electron. So you have to have an external source of electrons voltage to cause your electrolysis to work. Okay. Let's take a look at the case of the electrolysis of water. So what will happen if you try to electrolyze water? You force water to split up into hydrogen and oxygen. So at the cathode, you're going to have, remember, reduction, right? So 2 electrons here on the left side plus water. So you want to reduce water at the cathode. So if you did that, if you were to reduce water at the cathode, it's going to give you H2 and 2 hydroxides. Why is that? H2O, what's the 2OH2? Why is that reduction? What's the oxidation number of hydrogen in water? It's +1, right? H2 oxidation number is 0. So +1 to 0, that's a reduction. So the cathode reaction, if you're going to electrolyze water, the cathode reaction is the one that releases H2. Okay? So if you got typical setup for electrolysis of water is you have 2 tubes here. Okay? You stick a piece of metal there and then you hook this up to a battery. Okay, let me see if I can draw a better sketch here. So let's say I have a beaker of water here. Okay? I'll have a tube over here that has and then another tube over here. I'll hook it up to a battery. Okay, this is the positive end, the negative end of the battery. Okay, tell me, let's do a clicker question here. Where is the cathode and where is the anode? Did I stop the clicker? Oh, I still have it. Okay. All right, what's my question? Where is the anode? Is it A or B? Where is the anode? Is it at A or B? This is an electrolytic cell, okay? Where is the anode? Okay. Correct answer. The anode is in an electrolytic cell. The anode is positive, okay? Right here. So this is your electrolytic cell. Okay, this is a galvanic cell. Okay, you hook it up to a galvanic cell if you want to cause electrolysis to occur. So you want to cause a non-spontaneous reaction to occur. So the positive end here is your anode. Okay, and then the negative here is your cathode. All right. So where will H2 be formed? At A or at B? Where are you going to make H2? If electrolysis happens and water gives you H2, where will you make it? Will it come out in terminal B or will it come out in terminal A? What would H2 be in? What would the formation of H2 involve? Okay, the formation of H2 is, what did we say? Oxidation or reduction? It's reduction. It takes place at the cathode. Okay, so reduction of water to H2 takes place at the cathode, so the answer is B. Okay, so you form H2 over here, you generate H2 over here, you're going to generate O2 over here at the anode. Okay, so that's electrolysis. Now, so if you look up the standard electrode potential or standard reduction potential for H2O going to H2, you'll find it's negative 0.83. And at the anode, what do you form at the anode? Oxygen. So your water turns to oxygen. So this is the net ionic equation for that half reaction. You'll find that the standard oxidation potential for that is negative 1.23. Now, you can't look that up. What you look up is the reverse of that, and it will be plus 1.23. But since it's oxidation, you have to flip the sign. Okay, so it's negative 1.23. So what's your overall reaction here? Okay, you have two electrons canceling out, right? You have and remember, oops, they're not canceling out. 2 electrons versus 4 electrons. What should we have to do in order to balance this? Balance electrons lost, electrons gained. This has to happen twice, right? Every time this anode reaction happens once, right? So if you add, so I have to make this a 4 electrons, 4 waters, 2 H2, and 4 hydroxide. Okay. So overall reaction would be 4 waters plus 2 waters. That gives you 6 H2O in the overall reaction. Okay. Your 4 electrons are going to cancel out. And then you have O2 on the right-hand side. You got 2 H2 on the right-hand side. And you got 4 H plus on the right-hand side and 4 hydroxide on the right-hand side. Okay. So what eventually happens is this. Okay, so, okay, let me give you another clicker question. Which side will become basic as the electrolysis goes on and which side will become acidic? Where is hydroxide produced? At the cathode, right? So the generation of H2 will also give you hydroxide, and this will give you H plus over here. But eventually those two will mix. What happens? H plus hydroxide will just give you water. So the overall reaction here in the electrolysis of water will just be 2H2O. So these two will eventually cancel out, right? So the overall reaction is really just 2H2O yields 2H2 plus O2. So that's the overall reaction in an electrolysis reaction. Okay, so what is our overall cell potential? If you combine these two half reactions, what do you get? E reduction plus E oxidation, 0.83 and 1.23 add up to negative 2.06 volts. That means if you want electrolysis to occur, you have to apply more than 2.06 volts. So will a AAA or a AA battery work? A AA battery gives you how much? 1.5, so it's not going to work. Two of those in series would give you a total of 3 volts. That will work. Or you can get a 9-volt battery. You can get your electrolysis to occur. Okay? So in practice, you really need more than 2.0, significantly more than 2.06 volts to cause electrolysis to occur. So this is what we call an overpotential. It's similar to activation energy. There's certain minimum energy that they need to have to get the reaction going. Okay? And it depends on what the material you're using is for your electrode and what the reaction is. And like in the case of water, you need at least an extra 1 volt there. Okay? And also, since water is a poor conductor of electricity, you need to add an electrolyte to your water in order for you to carry out your electrolysis. So pure water, you stick it in there, it's not going to work. Okay, you need some electrolyte to conduct the electricity through the water. Now, the electrolytes that you add, if you want to produce H2 and O2, you want to make sure that those electrolytes are harder to reduce or oxidize compared to water, right? Because if you put something there that is easier to reduce than water, okay, instead of water being reduced to produce H2, it's the electrolyte that will get reduced. Okay? If you put something there that is easier to oxidize compared to water, instead of getting O2, that other electrolyte will get oxidized instead. All right? Now, so what kinds of electrolytes can you use? The cation from your electrolyte must have a much more negative reduction potential. It has to have a less tendency to get oxidized compared to water. So look at sodium, for example. It has an reduction potential of negative 2.71, whereas water has a reduction potential of negative 0.83, right? So more negative reduction potential, less tendency to get reduced than water, to get reduced, right? So in this case, we say we can use sodium ions as the cations for our electrolyte. That would be a good ion to use. If you look at the anions, okay, you'll find sulfate. It can be your best bet is usually sulfate. Okay, this is the sulfate can turn into persulfate. Okay, and the oxidation potential of that is only negative 2.05, which is significantly less than the oxidation potential of water, which is negative 1.23. Okay, so something like maybe sodium sulfate, you put that in your solution, that would allow you to electrolyze your water. Okay, and avoid having the electrolytes being reduced or oxidized instead of the water. Okay, so here's a clicker question. Which ion, if you're going to add electrolyte to your water, is least likely to get oxidized at the anode instead of water? So if you were to put that in your solution, in your water, okay, which of these is least likely to compete with water at the anode as far as oxidation is concerned? So fluoride, when it's oxidized, the oxidation potential is negative 2.87. Chloride has an oxidation potential of negative 1.36. And bromide, negative 1.05. Ready? So the answer is fluoride. Very good. The more negative the standard potential, the less likely it's going to happen. You're comparing what? Oxidation at the anode, 1.23 versus 2.87. Now, will chloride be oxidized? If you put chloride in water and you try to electrolyze it, will chloride be oxidized instead of water? Fluoride will not, right? Because it's more negative than negative 1.23. But what about chloride? Negative 1.36. Is it more likely or less likely than water to get oxidized? Less likely, it would seem, right? We predict that. But since we have to have an overpotential of an extra at least 1 volt, what actually happens is when you try to electrolyze water that has chloride in it, you get chlorine gas. Okay? Same thing with the bromide. And that's the process. Like if you have sodium chloride, brine is water that's rich in sodium chloride. And that's the way you can produce chlorine electrolysis. Okay? How about this? Which ion is likely to get reduced at the cathode instead of water? H plus or K plus? So we're looking at reduction potentials now at the cathode. Which one is less likely? Is likely to get reduced at the cathode instead of water if it happens to be in there? Is it H plus or potassium? So this is more likely to get reduced. Okay. Answer. That would be what? H plus, right? Why H plus? 0 is greater than negative 0.83. Negative 2.93 is very, very low tendency, right? So this is very unlikely. So the correct answer is A. Okay. So what you can do is, like if you put sulfuric acid instead in your water, what happens is at the anode, instead of water getting at the cathode, instead of water getting reduced, you're going to have H plus getting reduced instead, right? H plus from the sulfuric acid would get reduced instead of the water if you put sulfuric acid in your water, okay? Now, here's another question. Bromothymol blue is an example of what's called an indicator. It turns yellow if in the presence of acids, and it turns blue, it's colored blue in basic solutions. So if we carry out an electrolysis, where would we expect bromothymol blue to turn yellow? So if you did an electrolysis, okay, at one of these terminals, bromothymol blue is going to turn yellow. At the other terminal, it's going to turn blue. Where would it turn yellow? At the cathode or at the anode? Okay, it's going to turn blue at the. It's blue in basic solution, and what makes a solution basic? Hydroxide. So it turns blue at the cathode. Ooh. Correct answer is A. Okay? Blue in basic solution. That means where the hydroxide is being produced, that's where it turns basic. So that's where it's going to turn blue, and that's going to happen at the cathode. Okay? So if you carry out an electrolysis, you put bromothymol blue there, you can tell where the hydrogen is being produced and where the oxygen is being produced. You can tell which one's your cathode and which one's your anode.
Wait, the question was asking you which one turns blue or which one?
Oh, I'm sorry. Where it turns yellow. Okay, so the correct answer is, so where it turns yellow is where it's, I wasn't paying attention. Okay, where it turns yellow is where it's acidic, right? So acidic at the anode. Correct answer is B. Sorry about that. Okay, Faraday's law. says that the amount of a substance produced or consumed at an electrode during electrolysis is directly proportional to the amount of electricity that passed through. Of course, that makes sense, right? The more electricity you're passing through, that's more electrons. More electrons means more reaction, right? So unit of current, as we said before, is an ampere, is a coulomb per second. An ampere is 1 coulomb per second. And if you recall, the Faraday, we said, is 96,400 coulombs per mole of electron, okay? 96,500. The more precise number is 96,485 if you want more sig figs, okay? So let's apply that to this question right here. How much copper will plate at an electrode if your copper sulfate, you do an electrolysis of copper sulfate, okay? And you carry it out with a 1 amp current for 1 hour. So if you want copper to plate from copper sulfate, what's the half reaction here? Copper ions plus 2 electrons will give you copper, right? That's what you need to accomplish. So how much of the copper can you make to plate at an electrode if you do this experiment using a 1 amp current for 1 hour? Well, 1 amp is a coulomb per second, right? And you can see how many moles of electrons you have, how many coulombs you have per mole of electrons. So you can figure out how many electrons you have. Once you figured out how many electrons you have, you just divide that by 2. That gives you moles of copper, right? So let's do that. You're going to say, okay, moles of electrons would be equal to 1.00 amp is a coulomb per second. Okay, for 1 hour. This is in 1 hour. So 1 coulomb every second times 60 seconds in 1 minute times what? 60 minutes in an hour. Right? And it cancels out, seconds cancels out. How do you convert coulombs to moles of electrons? Use the Faraday constant. 1 mole of electron is how many coulombs? 96,485 coulombs, right? So coulombs cancels out. So that calculates moles of electrons. That would be how much? 60 times 60 divided by 96,485. Okay. So that was how much? 0.0373. 0.0373 moles of electrons. Moles of electrons per hour. Okay? And if we're doing 1 hour, then that is the moles of electrons. So that's per hour times 1 hour. So that gives you moles of electrons. So how do you calculate how much copper? 0.0373 moles of electrons. What's the relationship between moles electrons and moles copper? 2:1, right? 2 moles electrons per mole of copper. So 1 mole of copper is made every time you lose 2 moles of electrons. You use up 2 moles of electrons. That cancels out. So that gives you how much? 0.0373 divided by 2. 0.0187 moles of copper. And how many grams is that? What's the molar mass of copper? 63.55 grams per mole of copper. cancel it out. That gives you 0.0187 times 63.55, 1.18 grams of copper. Is that right? 63.55 times 0.0187, yeah, 1.19. That's how much copper you're going to plate. Okay? All right. That's it. One topic in your book that I forgot to add to the PowerPoint has something to do with corrosion, so let me just add that. Okay, corrosion has to do with oxidation of metals. Okay. So when your iron gets corroded, okay, what happens to your iron? It becomes Fe plus 2 or Fe plus 3, okay? And in Fe2O3, okay, you get rust, okay? And rust is really a hydrate, so there's water hydration involved there. So that's what happens to iron, okay? Now, if you look at aluminum, aluminum actually has a better oxidation potential than iron. But what do you know about aluminum? It doesn't corrode easily, even though it has a better oxidation potential than iron. And the reason for that is it reacts very quickly with oxygen from the air to give you aluminum oxide. It gets a coating of aluminum oxide, Al2O3. Okay, so the aluminum here is plus 3. So it actually has a very thin film of aluminum oxide. That's a very stable compound. That's the same material that sapphire is made of. Okay, so aluminum, if you try reacting aluminum, do some reactions with aluminum, you might think it's very reactive because it has a higher oxidation potential, but you'll find it's not. And the reason for that is you have to get rid of that very thin film of aluminum oxide over it before you can actually react. Okay, so what you have there is protected in a way by an oxide coating. Same is true with zinc, for example. Now, so one application of this is if you want to prevent rusting of iron, okay, what you do is you coat it with something that's similar to aluminum. Zinc does that too, okay? So if you coat iron with zinc, zinc has a greater oxidation potential than iron. So immediately, if zinc would give you a zinc oxide coating that protects it, that protects the rest of it from the effects of the atmosphere, oxygen. So if you coat your iron with zinc, you have what's called galvanized iron. So what you call galvanized iron, that's actually iron. Your iron nails, they're called galvanized iron. They're actually coated with zinc. So we say in these cases that zinc behaves as a sacrificial anode. Why is it called an anode? Oxidation is an anode reaction. Okay, so that's one application of electrochemistry right there. Okay, and you can look up the oxidation potentials for these, and you can verify those numbers. Okay, I think that's it.